Okay, so at this point in time, we should be able to easily split apart our periodic table into different sections. So we're going to call the first two columns plus helium our S sublevels, the last six columns minus helium, obviously, the P sublevels, the middle section right here, we'll call that our D sublevels, and this bottom section with the lengthanides and actinides will be your F sublevels. And remember, whenever you want to get the energy level for them, for the S and P sublevels, you'll use the row. So in this case, this is the first row in the S sublevel, so this is called 1S. This section right here would be called 2S because it's in the second row in the S sublevel. This would be called 2P because you're in the P sublevel and the second row, with the only two exceptions to this being the D sublevel and the F sublevel. For the D sublevel, you're going to use the rule n-1. So you're going to subtract 1 from the row, and that'll be the energy level of the D sublevel. So even though this section right here that I'm highlighting is in the the fourth row, it's going to be called 3D. You subtract 1 from it. And then for F, you're going to use the rule n-2. So you subtract 2 from the row. So the F orbitals here are found in the sixth column in in the sixth row. So you're going to subtract 2 from 6, and it'll be 4F. Okay. So now we're going to use this knowledge in order to write out electron configurations without having to do a bunch of counting or drawing boxes and diagrams. So in order to condense or simplify our entire configurations, we're going to use something called shorthand configuration. Now, what shorthand configuration does is that it pretty much just writes the electron configuration of an element by only writing the location where the electrons are found in and the amount of electrons found in said location. So we're not worrying about the spins of electrons, nor are we worrying about which orbital specifically those electrons are found in. And the way that we write the shorthand electron configuration is by first writing our sublevel. A sublevel can be something like 1s, 2s, 2p, 3s, etc. And then a superscript will show the number of electrons in said sublevel. So if I wanted to look at an example, this would be a perfect one. So here we can see that our energy level for our sublevel is the second one. The sublevel that we're working with is P. This can be either S, P, D, or F. It really doesn't matter. And then we have a superscript showing the amount of electrons in said sublevel. Remember that there is a maximum for each one. So for the S sublevel, you can have a max of 2 electrons. For P, you can have a max of 6 electrons. For D, you can have a max of 10 electrons. And for F, you can have a max of 14. So if you're ever working with an S orbital, you know that the maximum this superscript can be 2. If you're ever working with the P sublevel, the maximum this superscript can be is 6. For D, it would be 10. And for F, it would be 14. Remember that the entire time that we're working with the periodic table, we'll be using this notation. Again, remember, the first two columns are the S sublevel, the last 6 are the P, and the middle section is the D sublevel, with the bottom, the lengthanides and actinides, being the F sublevel. So, the rest of the video is just going to comprise of us just picking random elements and writing out the configuration. So, we'll start with a relatively easy one in carbon, which is right here, element number 6. Now carbon is found in the second row, or n is equal to 2, and it obviously ends in the 2p sublevel, the second row in the last 6 columns. However, based on the Aufbau principle, you must first occupy the first set of energy levels, or the first row. So whenever you're doing electron configuration, you'll always start at the top left, or the very beginning of the periodic table. So we're going to go ahead and fill up that first row. The first row is comprised of just hydrogen and helium, which will make up the 1s sublevel. Now the amount of electrons that are found in the 1s sublevel is going to be 2. You can obviously just count the blocks in order to verify that, so 1 and 2. So we put 2 electrons in the 1s sublevel. At this point we have completed the first row, so now we move on to the second row. The second row starts with these first 2 blocks, which are in the S sublevel and in the second row, so we'll call them 2s. And because of the fact that carbon extends all the way to this side of the periodic table, we know that this is going to be completely occupied, so you'll put 2s2. And then lastly, we reach the point where carbon ends, which is these last six columns right here. This is going to be called 2p because the last 6 columns of the periodic table are the p sublevel, and we're in the second row. And the one major thing that you have to focus in on is the fact that the p sublevel for carbon is not going to be filled up because carbon only reaches the second block. So whenever you reach the sublevel where your element ends up in, you're going to want to count the literal number of blocks. So it's going to go 1, 2. So carbon puts 2 electrons in the 2p sublevel. So the electron configuration for carbon is 1s2, 2s2, 2p2. Let's go ahead and do another one. So this time let's go a little bit lower and let's do sulfur. Sulfur is found right here in the third row. Now sulfur is in the third row, but again, you do always have to start at the very first row in the beginning. So we're going to start right here. Whenever you're doing electron configurations, you will always start with the 1s sublevel. So let's go ahead and occupy the first row. That's only comprised of a 1s orbital, and that'll have 2 electrons in there. We finished the first row, so now let's move on to the second one, which is just comprised of a 2s sublevel and a 2p sublevel. So you'll write down 1s2 because that's the amount of electrons that are placed there, and then 2p, and you can put in, oh, my mistake, 2s2, 2p, and you can put in a maximum of 1, 2, 3, 4, 5, 6 electrons, so 2p6. We have finished the second row, but we haven't reached sulfur yet, so we're going to go on to the third row, which is comprised of the 3s sublevel. You'll put 2 electrons, and then this is where sulfur ends up in. This is the 3p sublevel. And in order to figure out how many electrons sulfur puts in, you'll just count the blocks. So it'll go 1, 2, 3, and 4. So sulfur puts 4 electrons in the 3p sublevel. So this is the electron configuration for sulfur. Let's go ahead and do one more configuration, and that should do it. So we're going to look at something like copper, which is found in the D sublevel. Copper's in the fourth row, or n is equal to 4. However, we do have to start at the very top, so we're going to work on the first 3 rows before we even touch the fourth row. So starting here, this is going to be the 1s orbital, and you can put a max of 2 electrons there. That completes the first row. Then you move on to the second row, which you have the 2s and the 2p sublevels, which are going to be completely occupied. So it'll be 2s2, 2p6. You've finished the second row, so now we move on to the third row, which is comprised of the 3s sublevel and the 3p sublevel, both of which will be completely occupied. So it'll be 3s2, 3p6. And now finally, we've reached the fourth row, which is where you'll find copper. Now, these first 2 blocks are going to be the 4s sublevel, and we know that they're going to be completely occupied because copper is all the way here. And now the final sublevel is this right here in the D section. And it's very important that you remember that when you're working with D orbitals, you go with the rule n-1. So this copper is found in the this D sublevel is found in the 4th row, but you're going to subtract 1 from it. So it's not going to be 4D, it's going to be 3D. And then you would just count blocks like usual. So it'll be 3D, 1, 2, 3, 4, 5, 6, 7, 8, 9, which is where copper stops. So you're going to put 9 electrons in the 3D sublevel. Okay? And that's really going to do it for electron configuration. You can basically just pick any element on the periodic table, point at it, and run through the electron configuration just by using this same exact method. Okay? That'll do it for today.